We have seen how to bias both NMOS and PMOS transistors at a given current, and in the NMOS case we have also seen the current mirror structure, which can be used to realize a number of current sources starting from a single current source. Now we will look at a general biasing structure that is commonly used in an integrated circuit to realize a number of current sources of both polarities. Okay, so first we'll look at the PMOS current mirror. And as with NMOS, we start with a drain feedback structure where we connect a current source I0 to the drain terminal of the PMOS to sense the difference between ID and I0, and we know the usual stuff that ID minus I0 will flow into this capacitor and change the voltage, and that voltage can be fed back to the gate of the transistor. It will be in the correct direction to counter the difference between ID and I0. In other words, it will be in negative feedback. And now this VSG, that VSG would be equal to the threshold voltage plus square root of 2 times I0 divided by mu p Cox W by L. Okay, so this is nothing but the current factor. If you have a set of identical transistors, usually you do have them on an integrated circuit because they are fabricated at the same time and they are very close to each other and they are likely to be at the same temperature. Okay, if you replicate this VSG across another identical transistor, I'll call this M0 and M1, and I'll write M1 equals M0 to mean that they are matched. Then as long as M1 is in saturation, okay, let me show something connected to the drain of M1. As long as this VD1 is such that M1 is in saturation, this current will be equal to I0. Okay, obviously here I've ignored the effect of lambda. If you do have lambda, the current here will be slightly different from the current there, depending on how different the drain voltage here is compared to the drain voltage there. Okay, and it's not just one copy, you can make a number of copies. Again, I'll draw a line through the gate. It simply means that it's connected to this gate and also it comes out here. Okay, so you can have more transistors and more copies of I0, and it doesn't have to be just I0. So let's say all these transistors have a width W and a length L. Okay, then they'll have a current I0, and if you make a transistor of width NW and the length L, it will have a current of N times I0. So you can also have a multiple of the current that you started with. So this is how you realize current sources of a variety of values. Now one practical constraint which I won't elaborate here is that when you do have current mirrors and you want to realize different current values, you change the width, but you do keep the lengths of all transistors the same, because this inverse proportionality to L is not exact. Okay, doesn't matter whether it is inversely proportional or has some other complicated dependence. As long as they all have the same L, if you have N times W, you will get N times the current. Okay, for all transistors you use same length. Okay, now we have these currents, but this is still not like a current source whose both terminals are accessible. If both terminals are accessible, if you want to pull current from a node, you connect this. If you want to push current into a node, you connect that one. Okay, whereas here this terminal is the supply voltage and it's not useful as a current source terminal, only this terminal is useful. So with PMOS transistors you can only push current into a node, but you already know that with NMOS transistors you can pull currents out of a node. So if you want both, all you have to do is the following. So let's say you take one of these copies, let's say this is W by L, so a current I0 will flow if it is in saturation region, and you realize NMOS current mirror and as many copies of it as you please. Okay, so let's say this is Wn by Ln. If you have the same dimensions and this transistor is in saturation, something has to be connected here. I'll just show it as some load. As long as it's in saturation, this current will be I0, and again you can have multiple copies also with different dimensions. So let's say the width of this is m times Wn and the length is Ln, then this current will be m times I0. Okay. So you just have a bunch of PMOS current mirrors and NMOS current mirrors. Here I started with PMOS, but you could also do the other way around. Okay. And this structure is very commonly seen in every integrated circuit because you have a number of components, in fact a very large number of components where you need these bias currents. Okay. And all these bias currents are generated using transistors. Okay. In all the circuits that you saw, we had transistors biased at a constant current in our amplifiers and control sources because that was a good way of biasing. Now you know where the current sources come from. Okay. So if you want a current being pushed into some node, then you use this type of PMOS current source. If you want current pulled out of some node, you use this type of NMOS current source. Okay. So this is part of every chip, and if you start with a single current source I0, you can get a number of current sources of both polarities, of both pushing in and pulling out. If you want to be very precise about it, this is called a current source because it sources current into a node, and NMOS stuff is called a current sink because it sinks current from a node, but it's quite alright to call both of them current sources. Okay. Now how do we get this first one over here? Now there are many techniques to do it, and I won't go into all the details. One possibility is simply to replace this with a resistor of the correct value. Okay. So that you get I0. But the problem with that is that as the transistor characteristics change or as the supply voltage changes, the voltage across this will change and the current will change, even if the resistor is very precise. Let's assume that the resistor is very precise. It has to be to define the current accurately. Even then, as the voltage across it changes, the current will change. Now that also can be fixed by using a more sophisticated version of this drain feedback biasing. Okay. So how did we do drain feedback biasing? We had our PMOS transistor. We connected a current source to the drain, and we saw that the variation required at the gate is in the same direction as the variation that we see at the drain. So we fed it back directly. But as I mentioned before, it doesn't have to be fed back directly. It could be through any kind of stage which has a positive incremental gain. Okay. After introducing the exact topology, you can analyze and make sure that this is in saturation. Now one such possibility is an op-amp, which in fact we have used for some other types of constant current biasing. So how do we use an op-amp? So let's say the op-amp is here. We can feed back to one of the terminals of the op-amp, and the other terminal can be connected to some fixed voltage. Let me call it VD0. Okay. Now we want a positive incremental gain from the drain to the gate of the transistor. So this should be the plus terminal and this should be the minus terminal. By the way, you can, after looking at this topology, go back and analyze and see what the signs of the op-amp should be, and you will see that they should be positive. Sometimes students make this mistake of assuming that wherever the feedback is returning to, that is the negative terminal, but that's completely arbitrary. You don't know how many inversions are taking place inside the feedback loop. So you have to actually break the loop and analyze the sense of feedback and assign the signs correctly. Okay. So fine. Now again, the same thing happens as before. If the drain current is different from I0, the difference will flow into this parasitic capacitor ID minus I0. If ID is too small, then current will be pulled out of this and this voltage will fall down. As this voltage falls, the gate voltage of the PMOS transistor falls, and therefore the VSG, the source gate voltage, will increase, increasing the current. Finally, steady state is reached when ID equals I0. Then obviously VSG of the PMOS transistor has to be equal to the threshold voltage plus the required overdrive voltage. Okay. Now that is fine, that part you know already. But what is so special about this circuit? Because we have an op amp, and let's assume it's an ideal op amp, these two terminals will be virtually shorted because of the negative feedback loop. So this voltage will be exactly equal to VD0, and it's independent of the supply voltage and transistor parameters and so on. Okay. So now if you replace this current source with a resistor R0, the current flowing here will be VD0 by R0, VD0 by R0. Okay. And so if this voltage is precisely fixed, then this current is also precisely fixed. Okay. If the voltage and the resistance are precise, the current will be precise. Now you can use a precision resistor here because it's just one resistor, and with this one resistor you get accurate current sources all over the chip. Okay. And it turns out that a precision voltage source is also available in IC technologies. There is a circuit I won't go into. It's known as a bandgap reference, and its output voltage turns out to be the extrapolated bandgap of silicon at 0 Kelvin divided by Q. Okay, that's approximately 1.2 volts. You know that the bandgap of silicon is around 1.1 volts or so, but that's at room temperature. The extrapolated bandgap at 0 Kelvin is 1.206 electron volts, and the output voltage of this will be equal to that voltage. Okay, and that will be very precise. It's independent of temperature and so on. Okay. So that is what is used in a chip to get all these multiple current sources. The biasing circuit on a chip could look like this. This is the bandgap voltage, and you have one precisely defined resistor. It's either external to the chip or inside the chip and trimmed to have the correct value. And then this voltage will be Vg0 by R0, and you can replicate the same VSG across many transistors to get copies of the current, and you can also get a number of current sinks by using NMOS current mirrors. Okay, and especially with a MOS transistor, because the gate current is 0, there really is no limit to how many transistors you can connect. Okay. So this is how you generate bias currents on a chip. Okay.